So today, what I was going to do, mostly not just today, but this week as well, is that I was going to discuss like the gradient stuff, like gradient descent and all these things. Um, not just for tensors, but also matrices, because um, then I realized that probably matrix space, but most likely something you haven't seen before either. So I might as well use that as a motivating point. But actually, we can start with even something easier, but it's kind of like a quick scoring model to have. And you'll see how that's related to, you'll see how that's related to some of the other stuff I'll say this week. But okay, so let's start with the, I guess, right. For the last one. Yeah, you know, saying, our oh, right. With the Phantom Network, right? Yeah, I'll probably do it on Thursday, or am I sure today depending on how much time I have. Because I realized, okay, I'm doing it for transfers, but I still haven't said also how that works for matrix, right? And so I'll just do it for the matrix case, because that's a little bit easier to explain what's supposed to happen. Um, but yeah, no, like definitely that's where I want to head, but I think otherwise some of the issues will come out of nowhere if I start with the tensor. So I want to kind of show you that even with matrices, there's already like things that you have to worry about. That's why I want to do like a mini detour, which is still useful about what happens with matrices and all this stuff. So that I can assign some problems about that as well. But you can even start more basic than that, even with like a function of two variables. So if you have a function of two variables, right, let's say that the function has relations, you can take as many derivatives as you want. Um, so you to find the critical points, you would find the gradient, right? Like and set it equal to 0. And then the second derivative test was a way to classify the the critical points, right, as a local max, a local mean, or a sum. So it's always frustrating. When I teach this in Calc 3 because I cannot talk about eigenvalues, but so that you cannot really state it properly. So I'll state it properly so that you have like the correct formulation. So for the classification of a critical point with the second derivative test, what you would do is you find the Hessian matrix, right? So the Hessian was like this matrix of second partial derivatives, right? And the idea, if again, this is like the correct way to state it. If you look at this matrix, it's symmetric. That's the most important thing about it because like the mixed partial derivatives commute, right? It doesn't matter if you do x first and then y or y and then x. So this is a 2 by 2 symmetric matrix, right? And so because it's 2 by 2 symmetric, it has like real eigenvalues, right? It has one or two real eigenvalues depending on what the matrix is like, but it has like, so it has, let's say it has two eigenvalues, which may be repeated, but I'm just going to say like that it has two eigenvalues, lambda 1 and lambda 2, which may be repeated, which may coincide. Okay, so the idea is, so this was like this is the easiest way to state it. So So there are like basically four cases. Um, so again, like the eigenvalues are real numbers. So they could be both positive, both negative, opposite signs, or a different zero. That's how I'll say it. So if one is if one is positive and the other is negative, if one positive and the other is negative, that means that corresponds to a saddle point. So that means that the critical point would be a saddle point. To connect that to what you may have seen it as before, if one eigenvalue is positive and the other is negative, that means that the product is negative, right? Positive times negative is negative, and the determinant is the product of the eigenvalues for a matrix. So that so another way of saying this is that the determinant has to be negative in this case. And well, at least that's always like the way I say the second derivative testing count three. Like, you just look at the determinant and you will have like a negative number. But it's more because then the eigenvalues have opposite signs. That's really the better way to understand it. So you can have opposite signs, and it just happens to be the case that the determinant is the product of eigenvalues. So when you cannot use the word eigenvalues in count three, you can say it's like more concise way. Okay, so that is the case where one is positive, the other is negative. Another possibility is when both are where both our eigenvalues are negative. So if both eigenvalues are negative, that corresponds to the critical point will be a local max. So really like the example to have in mind is kind of like the upside down paraboloid. So let me just put, oh, by the way, I should put like the baby example for each case. So an example for the first one will be kind of like x squared minus y squared. If you look at, this is like a very simple case, right? Because they only have one at the origin. And if you look at the Hessian matrix, it's just like a diagonal matrix, like two, like, the Hessian matrix for this one is, for the first one, like the Hessian matrix is like 2, 0, 0, -2. And because it's diagonal, the eigenvalues are just a diagonal entry. So it's clearly the case there that, in that case, it's very easy to see that, like the determinant has to be negative. I'll just put the Hessian matrix right below it. Okay. Yeah. Well, if you have the spectral theorem, meaning that if you know that you can diagonalize, if you know that a symmetric matrix can be diagonalized, right? Then you diagonalize this matrix. Like, by the way, you only need to know that it can be diagonalized. You don't need to know that it can be diagonalized with an orthogonal matrix. But the idea is that H, where should I write this? Give me 1 second. So H can be diagonalized. But by the way, this is true in general, but like it's easier to see. It's easier to see in the diagonalizable case. If H can be diagonalized, you can write it as P D P inverse, right? Where like P is an invertible, and then you can take determinant of both sides, right? The determinant of H would be the determinant of P D P inverse, but that's a product of determinants, right? But the determinant of the inverse of the matrix is the same as is 1 over the determinant of the matrix P, right? Like, so this one is 1 over the determinant of P. So the determinants of P cancel. So you just get the determinant of a diagonal matrix. But in the diagonalization, what goes into this diagonal is are the eigenvalues themselves. So that gives you the determinant of D, which is just the product of the eigenvalues. So, this is a product of eigenvalues. That is the same way. That is also the easiest way to see the trace of a matrix is the sum of the eigenvalues. you do the same trick because the trace of A times B is the same as trace of B times A. So that allows you to kind of more or less you grow, I mean, you kind of run basically the same proof. I mean, you just swap the factors here. I mean, there are these more elegant versions of linear algebra course where you define that determinant as the product of eigenvalues, and then you just show that it has like the usual formula that you kind of like know and love. I mean, but that's a little bit of over. Yeah, so that is how it works in that case. And then if both eigenvalues are negative, the model, the toy example for that is kind of like this upside down paraboloid. So this is like the one you should think about, minus x squared minus y squared, which is like this salad bowl, the inverted salad bowl, right? And I mean, again, like the question is super easy to see in this case. It's like minus two, right? So like just to have like a concrete model in your head. And that is why you get like you get like the local math, okay? And if both eigenvalues are positive, that's the one that gives you a local mean. Um, so like an example is like the regular paraboloid, like the regular salad bowl, and again like the action in that case is 0, 0, 0. By the way, these kind of models are I actually do toy models, just kind of maybe to advertise the biological data analysis class of the spirit because there's a thing called like the Morse function where basically like only what I expect and effort if you take for class. But the idea is that like in a Morse function, like the critical points basically, if you do like a change of coordinates, if we find out like an appropriate change of variables, it's not like reaching to polar, but it can be more complicated than that. Then near a critical point, the function looks like one of these three kinds. So it's kind of like these are kind of like the toy models because every function locally or a Morse function like kind of like looks like one of these three kinds after looking at the variables. So it's kind of like what I'm trying to say is like if you understand these cases correctly, then you kind of like understand very well like the nature of like the critical points of a function. And Morse functions are basically the probability one of Morse functions, whole functions or Morse functions. So they're generic. That's kind of terminology for it. Again, I'll like get into like that like next semester, but that's like useful stuff to know. So that's it is not like a stupid thing to bring up these cases because really they are the building blocks for every other case. Like in every other like the more complicated situation, if you understand these, like you kind of know what happens in general. And then the last case, which you never really talked about too much in technology, but now I do want to talk about it is like the inconclusive case, right? When at least one of the eigenvalues is zero, like then the second derivative test does not work, right? So if one of the eigenvalues is zero, if one eigenvalue is zero, the second derivative test is inconclusive. And again, if one of the eigenvalues is zero, since the determinant is the product of eigenvalues, that means that in this case the determinant was zero. So you probably remember like that, again, this condition that the determinant was zero, but cannot classify the critical points using the second derivative test. And the idea there is that anything can happen, as in that, you could have like a max or a mean or a saddle point in that inconclusive situation. Otherwise, like, it wouldn't be that inconclusive if only one of the three would happen. So let me just show you like a quick example of each. You basically flatten out the paraboloids, meaning like I'll show, let me see if I have them on GeoGebra. Do, 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 do. So for example, again, like say this is like the standard, right? Like this is a standard paraboloid which has a mean at the origin. If you just flatten it by using x to the 4 and y to the 4 instead of x squared plus y squared, then now it kind of like looks like, like, yeah, it looks more flat near the origin. But it's still, I mean, because it's a sum of positive things, it's kind of like clear that the minimum would still be at the origin. You can also kind of like see it from the graph, right? And then if you turn it upside down, that would give you an absolute max, right? But it still wouldn't be detected by the second derivative test, right? You just turn it upside down. Boop, there you go. That there's an absolute max in the and then if you change one of the signs to this one, like it will give you kind of like a saddle point. Right? But you see, like it's always kind of like really flat near. It's really flat near like the critical point. Okay, so all that I'm saying is that, I mean, it's still not like the end of the world, right? It's not the end of the world. Either that it just like escapes the secondary test, which is fine. Um, and it makes sense because these are polynomials which are quartic. Right? So how can you use the secondary, like, second derivative, like, like they, like if you have something that starts with degree 4, like it wouldn't make sense as like maybe like the second derivative would be like convenient for that at the origin. But yeah, so this is not that bad, but you could have more interesting situations. Since I'm already here, I will show you the a different function. And this function, again, you'll see, I'm putting here the 1 just for convenience so that the graph is easier to see. Like really what matters is like the 1 minus x times y squared. But that way it will lift the graph by 1 unit, so it's a little bit easier to see on GeoGebra. Okay. So okay, so this is a graph of the function. Okay. And what I'm about to discuss it. But here, like, well, again, it's kind of like easy to see that there is going to be local mean, absolute mean actually, because it's being like a square, right? But the minimum happens along an entire hyperbola, So there is a family. Let me see if I can show you the curves. I don't know if you can see kind of like this black curve along all the points on the graph. That is where the minimum is achieved. So in this case, like the critical point, it's not like a single critical point. Like, you find an entire family worth of critical points, an entire curve. In fact, two curves, because like a hyperbola is kind of broken into two components. But so this is like a more problematic situation because you know, you don't find just like a finitely many critical point, but they come like an entire family. And this is like a basic model of like, for example, if you're doing gradient descent, or like a loss function or something like that, where you maybe get stuck. I mean, just imagine a more complicated value where maybe you get stuck at local mean and then you cannot move forward, or that you just get stuck in an entire like surface like of critical point, and like everything like stopped because the gradient, and there's no gradient to continue the gradient descent. So it is like a full model of like a representation, but I'll show you more realistically how this in a moment, like how this like a useful function to understand. So yeah, let me go back to the iPad. Oh yeah, sorry.
I guess like saying it's like all rolls into a valley. The valley's just flat for like
Correct.
miles. How do you know the seed spot under the bottom of the valley?
Well, I mean,
No.
well, I mean, uh, like for example, even in these cases with like x to the 4 plus y to the 4, right? you know, like, the gradient is still, you know, in that case, like, it still look very flat, right? But it's not that it's like literally flat, right? Because if you look at the gradient for those, you know, like there's still going to be some change in the gradient when you're away from the origin. But in this other one, oh, why is this? Oh, it's interesting that this looks kind of like yellow here. But in this other one, you know, like you could always like check, you know, if you're doing the gradient descent numerically, you know, you can first like, you know, it's always a little bit different there because there's always like approximation schemes with everything, right? So everything gets calculated and, you know, but you could always check whether like when you do the next step, you know, whether like the value of the function changes or not, right? If you're kind of like entering these regions, you know, where the function is more or less almost flat, right? Like, you know, it could happen that just because of like the rounding errors or all this stuff, like, you know, it looks like it got stuck, right? Like because of the value of like the change in the function would be so small, so tiny, right? That right, like it makes almost no difference. But you know, like it is, you know, it's in general, it's like a big problem, you know. All that I'm saying is like there are these situations where like, you know, there are multiple minima and that are not just isolated. The word for isolated, like isolated just means that it's on its own and there's no other minima around it. Or just like in general with the critical points and, you know, trying to understand the situation, there are like different schemes. I'm going to mention one of the schemes today, like actually, which is like an alternating like minimization problem, but I'm getting there in a moment. So, but yeah, like, but what I want to show you in a moment is like that function that I just plotted on GeoGebra. It is a very natural function from our perspective, but you'll see why in a couple of minutes. But let me just like write it down so that it's like a bit more, just to so that you see it's like a more problematic example. So if you had like, again, the one that I had added at the beginning was just like, so that the graph would look nicer. Like it really like the issue is like in the function itself, right? So if you look at that function, you know, this function, like, because it's just like the square of something, it's always one negative, right? So notice that f of x, y is always greater or equal to 0 and becomes exactly 0 at the hyperbola, right? And it's 0 when 1 equals x times y, right? Which is like y equals 1 over x. So that means that any point on this hyperbola is equal to global mean for the function, right? Which is what I was showing you. Any point on the hyperbola yields a global mean. And it's interesting again, here like from the perspective of it's interesting to see it from the perspective of the gradients, right? If you compute the gradient, also notice I mean, it's not a bad calculation to do. But you know, if you look at the gradient, you can kind of like see that if you're a point on the hyperbola, like, you know, like it's diagonal to hyperbola, when you kind of expect it, right? And the Hessian, if you look at the Hessian matrix, if you look at the Hessian matrix, this is the Hessian matrix at any point x comma y, whether it's critical or not. And let me write it down. But so at a point
on the hyperbola, when y is on the at a point on the hyperbola, a point on the hyperbola. You can replace y with 1/x in this matrix, right? So the Hessian matrix, it gives you 2/x squared, and then 2, 2 to x squared, right? And has determinant identical equal to 0. So at any point on the hyperbola, the determinant vanishes. And it actually has to happen because if the determinant is not, again, like I'll tell you that about next. If someone takes like the course next semester, I'll tell you that. But if the determinant is non-zero, then this cannot occur. Like the critical point is kind of like on its own. Like it cannot have like neighboring critical points like on its like annoying. They are isolated. But so like if you have like a family of critical points that like requires the determinant to be 0. But all that I'm trying to say is like that the second derivative test does fail miserably in this case, right? Because you have infinitely many global mean, and none of them can be detected, with the second derivative test. So it's like an example of where the things can go really, really wrong at any critical point on the hyperbola. Well, I'm going to tell you how this is so related to the matrices and the tensors. Okay, so how is this related? How is this function related to what we have been discussing? How is this related? This is related to our our topics. Okay, so let's go back to a very simple case, which is imagine you have like a 2x2 matrix, right? Let's say you have a 2x2 matrix, and let's say it has rank 2, because it's a square matrix, having rank 2, but that just happens whenever like the matrix is inverted. Okay, so let's say it's like a rank 2 matrix, okay, which has rank 2. This is a problem we already know how to solve, but I'm kind of like framing it in a way that connects to this secondary thing. So let's say we wanted to find a rank 1 matrix, which is the closest to this matrix, right? So you want to find a rank 1 matrix. So here's like the question, like the problem. Find a rank 1 matrix. I'll call the matrix B, which is closest to the matrix A. In what I will say closest in what sense, in a moment, like in the Euclidean norm sense, in the Euclidean distance, which is closest. So what does it mean? Like, remember when you come to matrices, you can find your distance. Yeah.
It's like SVD and.
Right. Exactly, yeah. We already knew the answer to this problem, right? Like, because like there's this Eckhart-Young theorem that I had mentioned that, if you had like a matrix of rank 100, what is the rank 10 matrix closest to it? Just like the matrix form out of the 10 singular values, like you take the SVD decomposition and you keep like the 10 largest singular values. And then that gives you the that gives you the solution. But now I'm pretending that I don't know the result, right? So I'm just trying to see it like from as a brute force calculus problem. What is the problem that you have to solve from a calculus perspective? Because it is an interesting problem because it's a non-convex linear optimization problem. And it is closer to some certain typical type of optimization problems that you have in machine learning and in tensor networks. So I'm kind of like framing it so that you see kind of from the calculus perspective how it looks like a terrifying, like a really like dreadful problem like that. So that's why having like the right angle on a certain problem can help you a lot. But so I'm just trying to do it like if you do nothing, like how do you attack this from a calculus angle? It's kind of useful to see. So, but yeah, like what does it mean to, say that it's closest, that the distance, right? Remember, there's like a distance between two matrices. So what you're trying to do is kind of like minimize this among all the matrices with rank 1, right? With at most rank 1. So you're trying to minimize, you want this to be as small as want this. It's like similar to a least square problem, right? If you think about it, but it's like for matrices, right? Want this to be as small as possible among all rank 1 matrices. Okay. Now I'm going to cheat. Just to set it up more like a problem. What does it mean to be a rank 1 matrix? It means that it is the tensor product of a single, like that you can express B as a tensor product of two vectors, right? That you could even do it by brute force. We actually had the problem on the guide without doing SVD. That if a matrix had rank 1, so I'm not cheating, right? Because I'm not using the SVD decomposition. Like I'm pretending that I forgot SVD, but like you can't prove that if a matrix is rank 1, then you can find the U&V. So that is totally fine. No, I'm not like there's no cheating going on. But since I don't know what UMV are, like let's say that the like there are two unknowns for U, there are two unknowns for V, right? And if you do the tensor product of U with V, so I'm writing it this way so that you think of them as kind of like traditional variables, from Calc 3. Right, if you do the tensor product of the vectors, like that's what the matrix would look like, right? So what is A minus B in this case? So A minus B would be, like you just subtract the entries. Right? Well, you don't have to work with the distance. You can just work with the distance squared. The people calculus create so that you don't have to take square roots, right? So that you don't have to keep track of square roots, right? Because if you find something that minimizes the distance, that minimizes the square of the distance as well. So you can just work. So the function that you're trying. So basically, you're trying to find the values of x, y, and w that minimize the following function. So we're trying to minimize. So we're trying to find the minimum of this function. The 1/2 is just for convenience when you take derivatives, right? Because there's a bunch of twos that are going to be coming out of the derivatives of squares. So it is Oh, sorry, I think the last one should be YW. Let's see. But it's just like, like you apply like the distance at the end, like the distance between two matrices, like the square distance between two matrices, it's kind of like the Pythagoras theorem. If you think about it, every entry of the matrix, vectorize the matrix. The formula that I have given you for the distance ends up being like the same as that. So it's just like kind of like the sum of the squares of the entities. So that's what we're trying to do.
Why are we squaring?
Oh, because otherwise you have to put square roots here, right? Like because Pythagoras theorem is with this, it's kind of like that's a usual trick when you're trying to minimize the distance, like I can do like an easier problem, right? If you're trying to find if you have a point here and you're trying to find right, if you're then you put it if you say this is at the point 1, 3, 1, 2, 3, right? And you're trying to find the point on this plane that's closest, that's closest to this point. You don't know what the plane is, what the point is in this color x, y, z. The distance would be, it's Pythagoras, right? So it would be the root of x minus 1 squared plus y minus 2 squared plus. But if the point minimizes if there's a point that minimizes the distance, it also minimizes the square of the distance. So the distance squared is just easier to work with because it has no square roots. And it's just easier to take derivative of one. And the two is just because when you take gradients and all of that stuff, there will be a bunch of twos that come out from. So it's kind of like easier because otherwise you have like a bunch of extra twos. No, yeah. So it's like a very common convention to put like a 1/2. That's also why the kinetic energy is 1/2 of mv squared. Well, I mean, not just the other reason, but just one of the reasons that like when you take the derivatives of that, things from that sort, like the v squared come out with 2, so it's kind of like convenient. You have like the 1/2 in front of it. Yeah, so the 1/2 is just for more aesthetic purposes. The squaring of the distance, that is something that is genuinely useful because otherwise you have like a bunch of square roots all over the place, and that makes like the problem like really really hard to track. But okay, I don't know if you can see like our function friend from before, because if you look what was like the function that you know that I was like that I had written before. If you look at one of these terms, right? Right, like our function was 1 minus x times y squared. That is more or less what you have here, but with different variables at it in every of the summands, right? And the ABC is like that's just like a rescaling, like there's nothing really important about the one here. Like I just put like a number to make it concrete. But all that I'm saying is that each of these summands it is more or less like that function that we were studying before. So each summand is like one of the uh like the function from before, like the function from before. From before. After relabeling variables, etc. There. Okay. And in fact, if you, like, but then, again, the thing is that if you try to, even just to find the critical points, it is a highly nonlinear problem, but the system of equations you have to solve is highly nonlinear. So it is like a bit of a mess to just tackle this problem directly, like, the gradient, I mean, I didn't compute, I kind of computed the gradient, but not in full generality, but, if you try to find try to find this is a highly nonlinear system of equation. You get some cubics or quartic. I mean, I think it's mostly cubics that you get. So you have to solve some cubics and all this stuff in the variables. This is a highly. And in fact, I may not have doing that, but it might not be a way to certify the secondary professor that I can found the mean or not, because we already know, again, that this was a problematic, function that the secondary test doesn't really work that well, right? So, and it still may be hard to certify. It still may be hard. Wait, give me a second. Yes.
I was thinking random. You like to project all of like the non-linear parts into like okay, one dimensional region and then put something. So
Well, so what I was going to mention now, it is not quite like a projection, but it's something similar like that. Which is kind of like okay, so it goes under different names, like block optimization or like alternating optimization. So the strategy, well, maybe I should try to kind of like say it in words first. And I think I should be able to start some of it now. But the strategy is like right now this function is like a function of like 4 variables, right? So what you do is like first you pretend that 2 of the 4 variables say are frozen. You start with a random point, like you start with some random values for z and w, right? A z naught and a w naught. Okay, so you forget that these are variables, and now you have a function of 2 variables. Okay, and then you try to apply just like the usual, finding the minimum to this function of 2 variables, right? That gives you a value for x and y, okay, which you take, and then you kind of like switch the roles. So now you use that value of x and y, which you freeze, and now you think of the function as a function of z and w, and then you try to minimize there, and then you kind of like you see why it's called like alternating minimization. So you kind of like go back and forth between alternating for one pair of variables and then for like another pair of variables, and that under certain situations does converge to, let's say, like a minimum. But the idea by doing it that way is that you do turn the problem into like a regular least squares problem, which is kind of like the cool thing. So globally, in terms of like the 4 variables, like the problem is like a gigantic mess. There's not really one way to solve it. And there's something like least squares that work. It's like a highly nonlinear problem. You're doomed to fail. But by doing this alternating method, you kind of like at each step you have like a least squares problem that you have to solve. Which is kind of like the whole thing, and that's actually the idea that we're going to do for the tensor network. So if it's, like the version of this is kind of like you have a tensor, you want to find a tensor that's closest to it of a small rank in, like, say, in the tensor frame decomposition. If you try to solve that directly, it's like a gigantic mess, because even already we made this like again, I supposed to get better with tensor, but you kind of like freeze one of the freeze all of the tensor except one of the bulk, like one of the disks or like one of the circles at a time. You minimize for that one, and then you kind of like do like a sweep out where you kind of like minimize one at a time. So That is probably the idea, which is really cool. And that is actually in practice how also looks like minimization things are tactic because you're gonna do like a direct approach. Now, just to kind of like right, so what just to put in words some stuff now. So so the strategy, so like you do like a more indirect strategy, direct strategy, where you freeze some of the variables and just try to minimize the problem with respect to the non like for non-frozen variables. So and try to minimize, find a minimum for an easier problem where like or where the function depends on fewer variables. Okay. And then you alternate, then you unfreeze the variables and kind of like alternate the scheme. And you unfreeze the variables and you kind of like go back and forth until you have again there's so and those and all of these things there's always some error or tolerance that you're willing to accept, so until you're kind of like close enough to the minimum or whatever. And then again I'll be more precise about this next time. But I do want to kind of like I still want to kind of like do this in a way that's slightly more general. So let me let's see what that. So if you see here, what I did is kind of like I regarded the mate, I was trying to find the matrix of rank 1, which was closest to A, right? But then I kind of like thought about the matrix in terms of like the actual entries, right? To see it as a function of like calc3, like of X, Y, and Z. It is useful to also just think about the function as depending on the matrix itself, as a function of the matrix, not so much like the individual entries. And then you do matrix calculus, like, how do calculus on matrices themselves instead of like the entries per se. So that is also useful to understand, and that's related to the tensor networks as well. So I'll explain how at least maybe like give you like a few 5 to 10 minutes basics of what we're trying to do. So we want is that a more elegant approach? Yeah.
It's calculus, isn't the same as like normal vector, like calculus with multivariable.
Well, right. It's just that okay, but the thing is, it's not like it's perspective because in the normal calculus, right? Like the variables themselves are like take only real values, right? In the matrix calculus perspective, like the variables themselves are matrices, right? Which is not what I did here, because when I wrote it this way, I kind of like turn the matrix into its entries. So it is equivalent. I'm not saying that you're going to get something magically different, but it's just like a different framework because that way you kind of like work with the matrix itself and it just simplifies some of the understanding of some of the functions, right? Because at the end of the day, everything that involves like matrices, you can always think about it as in terms of like the individual entries, but you don't have like a global perspective if you always do that. You know what I mean? So it's kind of like the same idea. But so I'm just going to do like a shift in perspective where I think of like the function as being a function of the entire matrix, not just like, the entries of the matrix. But, obviously you get the same answers. It's just that it's not as easy to identify the correct solution, you know. If you just look at it, because you get like a gigantic system of equations in terms of the entries, which is not hard, it's hard to parse out what is it saying. Whereas if you keep everything in terms of the matrices, you can like see very clearly, okay, this is supposed to be like a least squares problem or whatever. Like you wouldn't be able to see that otherwise. So yeah, let me kind of like at least show you what is the and also it kind of like gives you like a cool excuse to kind of try to talk more generally about how the gradient should be defined. Um, like in terms of like on a vector space, like where you don't necessarily think about it again. Using coordinates. So let me just kind of like give you like a motivation for the function that I'm going to try to talk about. So here's like the one that we'll start next time, and then also we'll talk about the tensor network gradients and all that stuff on Thursday. But so here's like a more general example or like a more general problem. No, it's not necessarily a square matrix, right? Let's say I just have like an n by n matrix. And you want to choose and then you choose a number r, choose r, an integer r greater or equal to 0. And you want to find two, so the goal is to find two matrices. You want to find two matrices. So U is going to be m by r. And V is going to be, okay, it's going to be n by r such that, okay, and here's my function. So you see, I'll think about it as a function of the two matrices U and V, f of U comma V, which is 1/2. Well, like, let me write it like this, actually. It's minimal. So that is more than the low rank problem, right? Because like if you think of the rank being like kind of like you're trying to find a matrix. If you just think about the SVD decomposition, right? Like now let's just cheat a little bit, If you think of the SVD decomposition where it was U sigma B transpose, right? And you kind of like absorb the sigma into B transpose or whatever, just so that you see it as a product of two matrices, right? So if this was n by n, this would be n by r, and then this would be r by n, right? So we know, right, like that if the largest are singular values, these, like the truncation of whatever this is will be the closest to A among all the rank R matrices. So what we're trying to tell us is find a matrix, find like the factors U of V that for you in this case. So it's kind of like the end, the low rank problem, but kind of like framed in this calculus perspective. But you see, and regarding this as a function of two matrices, right? That's kind of like the change in perspective. I'm thinking about this as a function of two matrices instead of like the entries of the matrix.
So we're assuming that matrix that we are going to be use to find the minimum is functioning as matrices.
Right. You already, but that is like, but yeah, but that's not, right, but that doesn't mean that is just because you assume that doesn't mean that you're like forcing. That on itself is not saying that those factors have to be like the one that come from the SVD, right? I just want that to be forced from like, from the minimization.
Where did you like the assumption that it had to be two matrices functional? Because like, what if it were How can we just say that 30 or 4? Like, anybody would-
Well, no, like you could do more, and that's actually in a sense what the tensor networks do too, right?
Oh.
Right. That's actually, because even for a matrix, that's actually like a generalization like of what a tensor network is, even for matrices, right? Where maybe you want three factors, right? And that is kind of like the rank in the tensor tree decomposition. Yeah, so actually that now you kind of like right, like you kind of like said a little bit of why this is related to the tensor networks, right? Because in fact, oh, that's actually a great question. Like, this is like, like, yeah, that is essentially in a sense what you do with tensor networks. It's just like now even it's not just for age, it could be for tensor, but it's kind of like, but right, like then you modify maybe maybe you have 3 or 5, but then there are contractions, right? Like they're not products per se, but they're like the contraction of the tensor along their common legs or what have you. But right, but this is kind of like the starting point, right? To the more general case, but it is already like a useful situation. Yeah.
Let's say you had some kind of like error or distance bound design. Is there a way to calculate the right R and where to go with that?
So yeah, there are methods that there are like, okay, so there are two types of optimization approaches. One where like you fix the ranks ahead of time, and there's like a more dynamic approach where the ranks are adjusted along the way, kind of like, minimize something, right? So you can have like both. Right now, I'm kind of like deciding the rank ahead of time, right? But there is more like flexible approaches where the rank is also open. And then I think I'll mention that as well, maybe if I have next time, of how we do that with the tensors, like, where you want to kind of like along the way, the scheme, we want to be able to adjust the ranks. And so, yeah, that can be done in both ways, yeah.
And then also, is there a way you can change the dimensions of the matrices where answers and into there while you're optimizing, or is that?
Oh, no, like, right, no, like, so yeah, like, it's easier to see it in the tensor case, but also kind of like give an idea of like how that happens. In fact, we would, no, but yeah, you can kind of like, yeah, you can kind of like be changing that along the way. Yeah, no, it's like, it is quite flexible. I guess that's what I'm trying to say. Yeah. But for now, yeah, I'm just kind of like, because this is how we started with the matrix perspective. It's more like I have my preferred rank in mind, rank 10 or whatever. Let's try to find the factors, right? But yeah, but there are great variations where you actually are adjusting the ranks along the way. Yeah. No, it's all very fine. Now, maybe just to kind of like as a segue for what I'm going to tell you about on Thursday, is that you would like to find the gradient of a function like this. But again, now as thinking about it in terms of the entry, like the variables being matrices themselves, right? So you want to define, like, well, I'll tell you next time is what the definition of like the gradient with respect to the matrix U should be, not with respect to the entries, like the global object, right? So next time we'll talk about what should like the gradient of this function. Kind of like the gradient with respect to the matrix. But that is going to be related to direction of derivatives. So I'm just kind of like give you a quick review of like how directional derivatives work in Calc 3, like just for 5 minutes. So the correct definition of the gradient is after you have like the idea of like the directional derivative. So this requires and so how does that have to be directional derivative? Because again, if you are in Calc 3, right? Say you were at a point P and you want to move in the direction of a vector V, right? Then the function, if you have a function, there's a rate of change
that the function experiences when you move in that direction, which that was called the directional derivative in the direction of the vector v, right? And okay, so there's like a very nice word for thinking, but right, you do like a dot product between the unit vector and v, right. Let's say the gradient of f, right? Which in our more fancy notation, like you would write it this way. No, so that is actually where the gradient pops out, right? Because you just start to do compute in general, how much does the function change in an arbitrary direction? And if you do apply the general, actually that's where it comes from. And we do the derivation from three. You can like see that gradient just right up here, all of the time. And so the cool thing is that you'll see next time that this is super easy to compute because it's kind of like a limit, like there's like a limit definition for the directional derivative, which is kind of like I'll mention it next time, but this is kind of like it's kind of like a partial derivative, but in the direction of the vector v. So it's like the regular limit definition of a derivative. Like what? Let's say. Well, here R is like X, Y, Z. I don't know, but the position vector. All that I'm saying is that a directional derivative can be very fine in terms of like a limit. So for this function, like what I'll do next time is kind of find the directional derivative for that function, and then that will suggest what the gradient should be defined as. And once you have that, like maybe I should kind of like give you like a preview of what you find. So what we will find next time is that the gradient of for that function that I found before. So that's what the gradient should be ends up being. And the idea is that, again, like you can just compute this in terms of like the individual tensor matrix, but you couldn't be able to identify it as clean as if you have this that way. Oh, sorry, no, you're right. It should be divided by. I just decided at the end, like last minute, let me just change it to T, but yeah, you're right. But I mean, yeah, like probably you saw it, like the Cup one definition of derivative is more with the H, so that's why I put the H in the end. So but again, I'll show you next time how that all works. Uh, another. And then we'll do a similar thing for the tensor networks as well.